Let us now illustrate with an example the calculations of n-step transition probabilities that we have just discussed. In this example, we are given a two-state Markov chain and as part of the input, the one-step transition probabilities between these two states. So, given that you are in state 1, the probability that you will next go to state 2 is 0.5, and the probability that you will stay in state 1 is 0.5. And given that you are in state 2, the probability that you will next go to state 1 is 0.2, and the probability that you will stay in state 2 is 0.8. Now, suppose that you start in state 1, and you would like to calculate the probability of being in state 1 after n transitions, or after n steps. With our notation here, this is R11 of n. That probability can happen in two ways. After n minus 1 steps, you end up in state 1, and then for the last transition, you stay in state 1, or after the first n minus 1 transition, you end up in state 2, and then you transition back to state 1. Assuming that you start again in state 1, and you would like to calculate the probability that you end up in state 2 after n steps, you could apply the same logic. But these are probabilities. And given that you started in state 1, after n steps you will either be in state 1 or in state 2. So R12 of n is simply 1 minus R11 of n. And this system of two recursions is enough to propagate R11 of n and R12 of n as a function of n. Let us do it and fill the blanks here. As indicated before, the case for n equals 0 or n equals 1 are simple and do not require the use of the recursions here. So, for example, for n equals 0, R11 of 0 will simply be 1, and so as a result R12 of 0 will be 0. And again, R22 of 0 will be 1, and as a result R21 of 0 will be 0. For n equals 1, these are the simple one-step transition probabilities. So you have 0.5 here, and 0.5 here, and R21 here are 0.2 and 0.8. The next cases for n equals 2 becomes more interesting. So to reach n equals 2, R11 of 2, two options again. You can go this way with the probability 0.5, or you can go from that to here with the probability 0.2. So here we obtain a total probability of 0.25, here probability of 0.10, and when you sum these two probabilities, you obtain 0.35, which is R11 of 2, and as a result you get 0.65 for R12 of 2. Then you can follow the same process for n equals 3, n equals 4, etc., etc. I will not do it here, but this would be an interesting exercise for you to do the next several steps, perhaps within an Excel spreadsheet. But suppose that I tell you the number for n equals 100, and I tell you that the number that you obtain here is about 2 over 7. So as a result, the numbers that you are going to have here is about 5 over 7. Let us then apply the simple recursions in order to find the values here for n equals 101. R11 of 101 will be 2 over 7 times 0.5 plus 5 over 7 times 0.2 will be 1 over 7 for the first one plus 1 over 7 for the second one, and so we obtain again 2 over 7. And if you do the same calculation, you will end up with 5 over 7 here. This is an interesting fact. When the system starts in state 1, the probability that I found myself in state 1 after a long period of time seems to converge to a constant value, in that case to the constant value of 2 over 7. Assume now that you want to do the same calculation for R21 and R22. In other words, you start in state 2 and you're interested in knowing the evolution of these R21 of n and R22 of n as a function of n. Again, I will let you do it. But I can tell you that these probabilities will also seem to converge to a constant, and in fact will converge to something that is exactly the same. 2 over 7 here, and 5 over 7 here. This is a second interesting fact. Irrespective of where we started, either from state 1 or from state 2, the probability of being in a state 1 after a long period of time seems to converge to the same constant, 2 over 7. So in some sense, for that particular example, the importance of the initial state vanishes as time goes by and does not influence long-term probabilities of being in any of the two states. Note that this is not true at the beginning, starting at state 2. The picture after few transitions will look different than if you had started from state 1. So the initial state does tell you something at the beginning, but this vanishes as time goes by. We describe these convergence properties by saying that the Markov chain eventually enters a steady state. What does this really mean? Does it mean that the state of the Markov chain itself becomes steady and eventually stops at a given place? No, the state of the system will keep jumping forever. What becomes steady are the probabilities that describe Xn. After the Markov chain enters steady state, then at any time, if you take a photo of the system and ask, what is the probability that the chain will be in state 1 on that picture? It will be 2 over 7. By the way, the steady state of being in state 2 is greater than the steady state of being in state 1. Does it make sense? Yes, state 2 is a little bit more sticky than state 1 in the following sense. When you get to state 2, the probability that you remain in state 2, which is 0.8, is greater than the corresponding probability for state 1, which is 0.5. So to conclude, this Markov chain has exhibited some nice long-term properties. Is this always the case for any Markov chains? Let us see.